All right, so this morning I think we spent quite a bit of time discussing about AI inference. I'm going to take this up a notch slightly because we are going to look at production grade systems now. And we are going to discuss the topic of distributed inference, why this is necessary. I'll go very quickly again through our key inference engine, which is LLM, but mostly to explain why we had to invest in scheduling and distribution, really to kind of get the max of GPU resources at production scale. And I'll present this new project, which is called llm-d, which was introduced earlier this year in May. And I'll explain what the community is doing. So first, to situate again the challenge with LLM inference, obviously the type of pattern in running LLM at scale is very different from traditional application system, microservice, HTTP type of request. By nature, when we run large language model, we are actually against a very autoregressive process, which is called decoding. The way that we basically produce language token needs the knowledge of past token in the production process, and that builds a lot of latency. In fact, with no optimization, such as the one that we've seen in engine like SGLang or VLLM, you would get by nature between 200 and 600 milliseconds per token of latency that's introduced by this process. So we need to optimize it. The second aspect is, if I ask you why is it difficult to do AI today as a developer, I think all of us, including myself, we are really struggling to get access to GPU. GPU are very expensive. So once you get hold of a GPU, you really want to maximize it. Unfortunately, it's very easy to maximize GPU with process like tuning, process like distributed data computing. In the case of inference, it's not. Typically, the type of request you run against an LLM, it creates some kind of bursty traffic, and it's very difficult to continuously affect requests for inference into a GPU as a batch. We also have memory management issue that is created again by the autoregressive nature and the fact we need to keep the context of requests and previously generated token. And unfortunately, when you start to look at the size of KV cache today, especially rising with kind of those long contexts that everybody now tries to use to pass as much information as possible to LLM, we are getting into a situation where KV cache grows to like 10, 12 gigabytes per request, just with context around 16K tokens. So that's extremely hard to manage. And the last bit is, on top of this problem that you have with a single model serving, obviously a lot of organizations, they start to have multiple model serving at scale, and they need to start sharing the GPU resources. But then also they need to deal with the problem of SLO management, right? Certain requests are more important than others. They need to be fulfilled faster. So how do you actually deal with that issue? I won't go too much into VLLM. We had a great presentation this morning, but obviously the interest of VLLM as an engine is it was actually built to address a number of the challenges that I mentioned. Specifically, and I'll be covering this very quickly, it provides a number of techniques like page attention, continuous batching, which really revolutionized the way that we think about LLM inference. In fact, most engines today that do inference have adopted those practices as well, so they are pretty standard, but we continually push the kind of optimization we do. One example would be speculative decoding that VLM recently released as a preview capability. With speculative decoding, we essentially have a much smaller model generate the token faster, while we still have a big model at the back to validate what the faster model and the smaller model is doing. So we are constantly pushing the boundaries at the kind of single instance serving level. The other advantage of VLM, of course, is agnostic to the hardware that we are using. Of course, you will see all the usual suspects like NVIDIA, AMD GPU. We've been working heavily with Google as well to support TPU and really maximize the use of TPU for inference recently. But if I'm focusing now on China, we now have a concept of hardware plugin in VLM that allows any GPU provider to essentially integrate themselves within the engine and self-certify and self-benchmark. So we are able now to support Ascend NPU or MetaX GPU as well with that project. So now let's move to two very important capability that VLM has implemented, and mostly to understand the capability of the engine before I move to the distributed aspect. So first is the KV cache challenge. So I've mentioned the problem of the KV cache is how do you maximize the memory usage? Traditionally, the problem we face is very hard to understand based on the KV cache utilization, based on the request, how much memory needs to be allocated. You'll see in this graph a little bit as an example, a typical strategy of memory management would be to over-allocate a slot for future usage while you are generating the token. Obviously, that results in a heavy fragmentation of the KV cache memory, and then you'll get out-of-memory challenges, or in the best-case scenario, if you still manage to generate your response, you will basically get 20 to 40% utilization of the memory, which is terribly bad. The solution that was brought then was called page attention. It's inspired by operating system management of memory, so virtual memory. And the idea, of course, is to have very small fixed size block that we call pages to really allocate the token in sequence. And instead of basically relying on a direct allocation for a single process, we eliminate the fragmentation by enabling flexible memory allocation. So what you see here in the middle, we now have a block table. The block table is capturing at any point in time where the generated token have been allocated within the pages. Yeah? So we just basically maintain a map of the previous token generation. The big advantage of this technique is that when you have reusable token, and that is always the case, to be honest, right? There's a lot of AI pattern where you have system prompt, which is essentially the same over and over, or you have an AI agent maintaining a context across multiple queries, you will get a lot of reusability of the cache by actually using this technique. The second really breakthrough technique that's extremely important is the continuous batching. In the traditional naive way of sending requests to LLM to the GPU, we basically use a static batching where we basically queue sequences until at least one of them is ready to fill the GPU memory, and then we send all of them at once. But obviously, again, as you can see, a lot of fragmentation and really not really great resource usage. With continuous batching, we dynamically aggregate all the incoming requests, and we make sure we keep the GPU pipeline full by continuously batching the request for decoding. So this is a system overview of LLM, right? High level. We have other capability. I mentioned speculative decoding. We also help to essentially reduce the model size by providing a number of model optimization techniques. Quantization is probably the most famous of them, but it's not the only one. We essentially try to reduce the model size by doing some mathematical optimization on essentially the model weight. We support tensor parallelism, so models that wouldn't fit in a single GPU. As you can see on the left, we essentially allocate multiple GPU and worker node of VLM, and we essentially strip the model weight across. We shard the model weight across multiple processing layers, and that enables us to essentially run across a huge range of GPU for big mixture of expert model, for example. The last bit is if you are a developer, VLM provides you with OpenAI API compatibility out of the box. So when you serve, essentially, you are getting completion API, chat API. You can straight away start coding. But so all of this is great. But now the problem is if you're an organization that operate maybe dozens of models across hundreds of applications, you are not going to be running single VLLM instance. Or if you do, that's going to be extremely inefficient. And the way we look at it is very simple, right? The first thing is from an AI perspective, the type of pattern that we have for LLM requests is typically 6 to 9 times more expensive compared to traditional application requests. And part of the challenge that we have is the type of pattern usage that we have with GenAI in particular. Here I show you just two simple patterns. If you think about a RAG typically has a very, very high input content, which will basically result in a heavy compute load under the pre-fill stage of a VLLM allocation. Whereas if you think about an agent that does thinking and reasoning pattern, you actually have a burst of very small requests that are actually going to the VLM. This would result into very different resource usage of a VLM instance. If this type of requests are allocated to the same VLM instance, we are going to face an issue to really do dynamic sizing and to manage memory and to manage really allocation. So the way we'll start to look at it is, could we actually think about a way to orchestrate and schedule requests to VLM instances that are a little bit more specialized? And in this way, we have better optimization opportunity by reusing the KV cache across multiple requests. And we start to be able to deal with scalability bottlenecks. So in order to do this, we decided to use Kubernetes. I think personally that if you look at Kubernetes 2 years ago, Kubernetes for AI was really the right platform for tuning, but it was very ineffective for inference. It was mostly useless. It was not designed to manage the type of workload that we have with AI inference. But in the past year or so, this has changed. We have had several working groups in the Kubernetes community to really specifically focus on the topic of inference optimization. Just to name a few initiatives, we have a group looking at standardized benchmarking. They basically started to look at patterns of GPU optimization and how to make sure we standardize the way that people will leverage hardware on Kubernetes platform to really optimize this type of workload. The most important one, though, is probably the next one, which is AI-aware load balancing. I think Kubernetes introduced some time ago the concept of gateway API, which is essentially looking at routing, layer 4 and layer 7 networking across Kubernetes cluster. And on top of the gateway API, the committee built an inference extension, which essentially focus on intelligently distributing requests to pod within Kubernetes that are doing inference. Last bit is the hardware portability. Now, if you, again, looked at Kubernetes a while ago, you would have to exactly allocate workload to specific GPU, specify the memory, and honestly, sometimes it's very hard, especially if you can't predict the usage pattern for inference. So what has happened is with DRA, dynamic resource allocation, we've built a way to really make the scheduling agnostic of the hardware provider or the infrastructure provider at the back. You can basically now specify type of inference instance and then just let the system decide for you. So all this is actually a very good precursor to start to build optimization in a cloud-native platform for inference. So here comes llm-d. llm-d is an open source framework for distributed large language model inference, and it runs natively on Kubernetes. It's currently powered by VLM, but you will see later it's actually agnostic of the engine you use. So you could, in the future, swap VLM by another compute engine. It's been designed to do so. It's obviously cross-platform as well. And as I speak, we already have a very wide industry collaboration on this project. The key contributor now are Red Hat, Google, and IBM Research. And NVIDIA, AMD, and CoreWeave have joined at the start of the project to contribute as well. But the community is growing very, very quickly. Again, it's actually a 4-month-old project. So what you are seeing here, to me, is very impressive because it's actually a lot of functionality in a very, relatively very, very short time frame. llm-d provides what we call well-lit path. So this is of interest to people in the audience who are essentially just bothered about running inference in production and you don't really want to worry too much about the detail. What's a well-lit path? A well-lit path is a way to standardize the deployment of the llm-d stack to deal with very specific inference challenges. One of them is disaggregated inference. It's actually focusing on situation where you have a wide range of different inference workload and you want to specialize the GPU between the prefill and the decode phase. So VLM gave us the possibility to do it, but it didn't give us an intelligent way to schedule the workload to specific pod doing prefill and decode, and it doesn't also tell us how much resource needs to be allocated. So llm-d builds this additional layer of intelligence to manage really this allocation. The second one is smarter scheduling with KV cache and load awareness. So this is essentially saying, build some awareness of how loaded your GPU are, and also what your KV cache actually contain, and then start to allocate intelligently the request to the right VLLM instance. And the last bit is the support of mixture of expert. So if you are focusing specifically on a mixture of expert model, and you basically need to start sharding the model over a very large set of instances and pods, this will basically do the job for you. This is the llm-d architecture. The way that we architected llm-d, for us, what's very important is what I call operationalizability. One big advantage of Kubernetes is we can automate the deployment, the day 0, day 1, and day 2 of the stack, which means that for someone who is not a platform engineer, you actually leverage the capability of the platform to manage the deployment and the management of the stack. How is it run when it's actually doing resource management at scale? This takes away the pain from you, which is great. The second part is obviously the flexibility. All you see here is composable. So we have an inference gateway that comes in standard, but if you have another project that is gateway API compliant, you can essentially swap it in. You can replace the component. So that's very important as well. And the last bit is you have to think of this stack as a performance management stack. What I mean by this is, and this doesn't really appear on this diagram, but when you deep dive in the inference scheduler, we basically support a scoring model that you can configure yourself and define your SLO policy for the engine to implement it in real time for you. So that's very important. It means even as an end user, you can come in the community and contribute SLO management policy as an example. You don't need to focus on the stack itself. Now, just to go through the three really performance management capability that this architecture provides. So the first one is we have disaggregated serving that you see here, right? We can disaggregate the prefill and decode across different instances. So there'll be Kubernetes pod with different GPU performing the prefill and the decode phase of the workload. The second one that we have is essentially the disaggregated memory management. We can basically strip the KV cache across different layers of memory depending on the priority of the caching. So essentially, pages that are more likely to get a hit in the cache can be prioritized to be kept in the memory that is faster to access. So that's the second one. And the last one that you see here is the variant autoscaler. What the variant autoscaler does is it dynamically manages the resource and memory allocation of the pod within the Kubernetes engine. I'll just go through those three capabilities to give you an idea. So the first one, of course, the very important one is the intelligent inference scheduling. And that is handled by the inference gateway. All inference gateway out there for cloud native are essentially based on Envoy. And you can use multiple of them. And typically what we are looking at doing is smart traffic direction. This is just an example of load-aware routing, but it's the same concept if you are doing KV cache-aware routing. What we have built is we have built a telemetry integration. We bring the telemetry data all the way to the gateway to take smart decision and allocate to the most likely instance where the queue is not too loaded and also where the KV cache has more ability to get a hit. So that's essentially what this does. The second one is prefill decode disaggregation. So here we really focus on the ability to do the prefill and the decode phase separately. And the reason for this is the prefill is compute heavy, while the decode tends to be memory heavy. So we really want to have dedicated resource in the cluster to handle them separately. In order to do this successfully, we need to be able to efficiently transfer KV cache between the different instances that do the pre-feed and the decode. In order to do this, we leverage the Nixle data transfer library from NVIDIA, which relies on UCX networking that allows us to manage all the different network transport protocol that you see here. The last bit is KV cache management. So for KV cache management, we basically have two ways to look at memory optimization. One is north-south, so it's essentially we use the GPU memory for the most likely pages to get a hit, and then we delegate to CPU memory or remote memory for the less likely data to be cached, but still keeping them available in case we need to recall it in the KV cache. The east-west cache management is used heavily in what I just mentioned between pre-fill and decode, right? So it's a way to use a remote storage across multiple VLM instances so they can actually share the data. This one is also required to create one single KV index globally across all your instances. And that's the telemetry we use to do intelligent routing. So this is really the end of my presentation. I really wanted to give you an idea of what the llm-d project is set to do. We are starting in this project. I'm here in China because we are actually discussing with a number of Chinese technology partners to also join the community and develop this project with us. You can easily join through this QR code that will drive you to a way to self-invite yourself to the community on Slack, and from there you can actually get started. Last bit is we have an event that will be on November 1st, which you can basically register for. It will be in Beijing in person, but we'll also run on WeChat, and we are expecting a lot of attendees. It's going to be a VLM community meetup, but we are really going to focus a lot on distributed inference for that particular session. Thank you for your attention.